If it is a tabular data, there is no second thought. Please understand, if it is a tabular data, whether I am predicting a rainfall or any continuous value, I'm predicting a sales value or some glucose level. For metric also, I'll just go with RMSE score or MSE score. No issues. That is more practically relevant value. But coming to this bounding box localization problem, the more practical and relevant metric, technically, please again and again, I'm telling you, technically you can free feel to give metric MSE also. But the main idea of metric is for how you are going to judge the model, okay, based on your observation. Okay, how model is going to learn internally, it is based on the loss function MSE, that is different story. But judging can be done with various scopes. For the classification problem, like how you judge the model in terms of AUC score, how you judge the model in terms of F1 score or precision, that's your choice. Similarly, for the bounding box, what is the best way to judge the model? Instead of using the MSEs for internal process, that is fine. For as a data scientist, as a human being, for the human perception, the best metric to judge the performance is IOU score. So again, this is something a new term for you. You are experiencing for the first time. It is called as a intersection over union. IOU. For the perfect matching, your IOU score will be 1. Now you understood what is the meaning of this IOU. Suppose if this black box also exactly overlap with this red, just for the ship example, suppose your MSE reaches 0, at that case, your IOU score will be 1, like an accuracy score for classifier, isn't it? When your log loss is 0, what is your accuracy score? 100%. But practically that is very less feasible, isn't it? So what is meant by that intersection over unionness? Intersection is, okay, whatever the shaded portion, I call that is the intersection. So let me try to explain the formula, okay, diagrammatically. Okay, then I will talk in terms of quantitatively, we'll try to discuss that. So the red one is the expected and the black one is what? The observed value. So the intersection is, this is the shaded area. It's the area in terms of pixels. Please understand, this calculation is done based on pixels. Now you understood the importance of metric. Now the metric is more application specific judgment, isn't it? I wanted to make a more application specific judgment, because this application is more related to the computer vision. So the judgment also, if I go with like a metric which is more relevant to images, more relevant to the pixels, that could be a better metric rather than technically. Even MSE also still sounds good, but this which will be more relevant, I just go with that metric, which is IOU score. So this shaded area is called the intersection area. So we need to compute the intersection area. So how to mathematically compute that area, that is shortly we are going to see. The first I try to explain the formula in a diagrammatic logical perspective. Over union, right? Intersection over union. That means in the denominator, we need to substitute the union. So the union is this. So the shaded area full union. See, while calculating the full area of the black box, let us assume the area of the black box is A1. Okay, the area of the red box is A2. Let us keep this area calculation, intersection area calculation is capital I. Okay, capital I is the intersection area. This is A1, this is A2. The area of the black box, the area of the pixels occupied in the red box is A2. Listen carefully. While calculating the area of the black box, okay, I include this intersection area, isn't it? My intersection area is included while calculating the area of the black box. Similarly, while calculating the area of the red box, once again, this portion is included, isn't it? That means my intersection portion is being included 2 times. While calculating the black box area, this shaded portion is included. While calculating the area of the red region, red box, there also this portion is included. That means this area is being included 2 times. But strictly speaking, according to the formula, what is the union? Union, it is the area which is put together area this much. So what should I do? A1 plus A2 minus I. Because I know this overlapping area, already I computed in capital I. Okay, so A1 area plus A2 area minus I, because I is included 2 times. So I need to subtract 1 time. So why I subtract 1 time? Because this guy has been already introduced to 2 times included. Got it? Why I do this A1 plus A2 minus I, the denominator. In the numerator, okay, computing A1 and A2 is very straightforward, isn't it? Computing A1 and A2 straightforward. Let us see how to compute this. First, we'll calculate the area of the the red expected box, the ground truth. So for the ground truth, we know the coordinates. So we know the top left and bottom right coordinate. Let us assume this is my x1, y1, this is x2, y2. If I know the ground truth coordinate for this object, what is my area? Area is nothing but width into height, isn't it? Width into height. From x1, y1 and x2, y2, can we easily compute width and height? What is my width and height? Just absolute difference of. Why I use the absolute difference? Either you substitute x1 minus x2 or x2 minus x1. Okay, so for safer side, I just put absolute difference of x1 minus x2 or x2 minus x1 into y1 minus y2 will give me the height and width. So that is going to give me the area. And what is being trained is somehow your model has learned this black box. So this is the actual, but your model has learned something else. So for this black box, some other x1, some other y1. Okay, some other x2, some other y2. Once again, I calculate x1 minus x2 difference into y1 minus y2 difference, which gives me width and height. I compute this area. So calculating the area for A1 area and A2 area is very straightforward. Intersection area, let us see another example, how to compute this. Now we try to calculate the numerator part. So the denominator, we calculated A1 plus A2. Okay. We need to subtract the intersection, right? To literally to complete my denominator calculation. So far in the formula, I just computed A1 is computed. A2 is computed, minus I need to subtract something, right? If I know the intersection value, okay, I can substitute this guy here, okay, minus this intersection. So now we are in the process of computing this capital I. A1 is done, A2 is done. So how to, once I know this intersection, I can substitute this in the numerator, I can substitute this denominator. See, the idea here is, see, if your ground truth and the predicted value, bounding box, are exactly same, okay, what is my total area? Total, this A1 plus A2, okay, that means the same area, right? This area. My intersection area also the same, right? My numerator and the denominator will occupy the same number of pixels if it is 100% matches. My intersection, what is my intersection? This is my intersection, the full portion, divided by, what is the union portion? My union portion also, it's a 100% perfect match. For 100% perfect match, it's a union. Okay. So numerator and denominator area same. So your IOU score is 1 for a perfect match. So practically we don't get a perfect match like this. So we may get IOC score like 0.7, 0.8 like that. So very practical scores are in the range of 0.9 and all, very rare, or very, very rare cases. Most practical scores of IOC scores are somewhere around 0.7 to 0.8. Most business problems we may get. Even for this level of IOC score, your model will be behaving very reasonably good, very well localized without losing any region. Okay. Maybe some extra background region from the ground truth, maybe additional extra background region. Maybe your ground truth will be very precisely will be there. So if that level of tuning is required, means you need several lakhs of iterations required. So people use some compromise, even with IOC score of 0.7, 0.8, is more practically viable result. They can take it for the deployment. See, at the end of the day, phase has to be recognized. Okay. So with extra 2 rows above the top. Okay, this is the perfect ground truth. Maybe if your model has extracted a little bit extra, definitely it is going to affect your IOU score marginally. So now let us calculate how to calculate this intersection area. So the red one is the ground truth, means expected. Okay, this is expected and this is predicted. So the black one is predicted. Let me name this coordinate x1, y1. This is x2, y2. This is x3, y3, x4, y4. So to calculate this area of the intersection, first of all, I need to know this coordinate, isn't it? I need to know this coordinate and this coordinate. If I know this coordinate and this coordinate, it's easy for me to compute this area of this intersection. Okay. So how do we get this coordinate? So better I will take a numerical value for the better interpretation. We'll take that ship coordinates itself. Okay, the ship coordinate, the ground truth value, let me take top left is 200 to 50. Okay, this is 200 to 50. 200, this is 250. And the bottom right is 600, 400. This is 600, 600, this is 400. Oh, sorry. This is ground truth, right? So I should mark 600, 400 here. I should erase this. So this is the ground truth, 200 to 50, 600, 400. Let me give some value to this model, what it has learned over here. Look at this. This is 200th column, right? X3 means 200th column. It spans from 200th column to 600th column. That means your model has predicted something X1, okay, which is very far from the actual 200. Maybe I'll say 100, okay, bit early. It says 100th column onwards, the object is available. But in the originally, our object is available from 200th column onwards. But model says that, hey, the object is available from the 100th column onwards. So 100th column. And similarly, it says that from 100th column, it goes up to, I'll say 400. Sorry, 500. 500. As per the ground truth, our object is available from 200th column to 600th column, but model has learned 100th column to 500th column. Some deviation is there. Similarly, the object is available from 250th row to 400th row. But model says something. The model says that our object is starting from maybe 250, I'll say, maybe 150, I'll say. It starts much earlier, 150 to 300. Okay. So what is the general logic? I can use it for this intersection point. There are two intersection point I need to compute, right? The one intersection point is this. This is the one intersection point. Another intersection point is this. Can we use some general logic to find out? Obviously, this is 200. How algorithm will do in a generalized manner is, it will compare the top left coordinate of the ground truth and the top left coordinate of the predicted one. and your intersection has happened much after this 100, right? After 100th column, 200. After 150th row, 250th row. So it uses the max logic, max of x1, x2, max of x1 and max of x1 and x3, x1 and x3. It will pick 200. Okay. And similarly, max of y1, y3, it is going to pick 250. So obviously, this is the intersection point is recorded as 200, 250. So how it will record this intersection point? It compares x2, y2 coordinate with x4, y4 coordinate. It uses the min logic, isn't it? Min of x2, x4, min of y2, y4. So 500, 600. So 500. Here it is 300. You may think, okay, what will happen if suppose if the model has predicted the bounding box something like this, instead of the top side, suppose it has predicted the bounding box something like this. Even for this case, this is the intersection point, right? Intersection point. Your intersection point, when compared when you are comparing this coordinate with this coordinate, and similarly the bottom right coordinate with this bottom right coordinate. Obviously, the column number, if you consider the column numbers, if this edge towards the left hand side, this edge happens towards the inverse side. So always I should take the maximum will get you this edge. Similarly, the inner edge, whenever you compute this inner edge, because when compared to the ground truth is always happen to the right hand side, so the minimal value will fall in the inner edge. So the one side of the edge, it takes the maximum value, another side of the edge, it takes the minimal value. So once I have got this value fixed, now I can easily figure out what is the difference, and I can take the area. So this x2, this value minus this value, and this value into this value minus this value, you can find out the area covered in this box, which is nothing but 300, 500 minus 200 into, of course, absolute value into 300 minus 250. 300 into 50, which is 15,000 pixels. So this overlapping area, this intersection area, it overlaps 15,000 pixels. So that is what the intersection area, that intersection area should need to be